Our last talk in this session is Emily Howerton.
Okay, so before I get started, I just want to say thank you to the organizers for this opportunity. As you heard from Katya, I'm a graduate student at Penn State, but I'm also a member of the COVID-19 Scenario Modeling Hub Coordination Team. You heard a really great overview of that project from Rebecca Borchering earlier this session. So the work that I'm going to be talking to you about today really grew out of the Scenario Modeling Hub and the things that we were thinking about, but I think that the methods and the conclusions are actually much more general. So I'm not sure I need to convince anyone in this room, but when we have these really important and urgent infectious disease problems, it can be quite useful to have predictions about the future from multiple independent infectious disease models. And what we've seen across infectious disease forecasting settings, as well as in other fields like weather and climate, is that the aggregation of these predictions is actually more robust and reliable. Now, there's many different methods that have been proposed about how we do this aggregation, but it turns out deciding which method is best for your particular setting is actually a really hard problem, and it turns out that this problem is harder for scenario projections. So if we think about short-term forecasts for a second, oftentimes in these settings, how we decide on an aggregation method is we take a bunch of different methods and we test them. Because the horizon of our forecast is relatively short, here it's 1 to 4 weeks, we have this very fast feedback between observations and predictions that we can use to decide which of the methods is working best. But in the case of the Scenario Modeling Hub and scenario projections in general, we're making predictions 6 months into the future, and so this feedback is slow at best, and sometimes it's really not feasible at all. So to talk you through how we thought about this problem and some of the methods we considered, I'm going to use just a toy example. So let's imagine for a moment that we are public health officials and we need to decide whether or not to start planning for the potential need for a field hospital over the next 6 months, let's say. We know in our jurisdiction there are about 15,000 hospital beds, and if our risk of exceeding that bed capacity is more than 5%, we're going to start the planning process now. So as the decision maker, we can sort of make this decision in many ways, and one of those ways is to use predictions from multiple models. So I think the graph is not coming up here, but imagine there are 2 probability distributions. And if we have 2 probability distributions, we can think about maybe using one of, and those are the model predictions, we can think about using one of those model predictions, maybe let's say the model that we trust more, and we can use that to make our decision. But in doing so, we're sort of ignoring or not using all of the information that's available to us. The alternative is to aggregate multiple predictions. And to do this aggregation, I need to answer 2 questions. The first of those questions is how do we combine the predictions or aggregate or average them? The second question is when we do this combination, how do we weight them? Today I'm just going to focus on the first question, which is how to combine them, but please feel free to ask questions about the weighting as well. So to understand the difference between the various methods that are out there to aggregate these probabilistic predictions, so full probability distributions, we need to look at the cumulative distribution function. So here, imagine model A and model B are the 2 models that we have at our disposal to make our decision. The first method that we could use, or general class of methods that we could use, is called quantile averaging. So for quantile averaging, I take a particular quantile or cumulative probability on the y-axis, and I average the values of peak hospitalizations across each of the models. If I do this for each of the quantiles, then the aggregate distribution I get is shown here in orange. This is also called the Vincent average, if anyone is familiar with this literature. Now, the alternative method is called probability averaging, and to do probability averaging, I take a particular value of peak hospitalizations on the x-axis, and I average the cumulative probabilities from each of the models. And so if I do this for each of the values of peak hospitalizations, I get the aggregate that's shown in blue. And it's not really clear that these 2 ways of averaging would give us different aggregates, but clearly the orange and the blue lines don't look the same. And if I switch from the CDFs, which were shown here, back to the PDFs, we can see that the 2 ways of aggregating give us, in fact, qualitatively different aggregates. So this was the 2 individual distributions you were supposed to see a few slides back, in the black. And in fact, so this qualitative difference in our aggregates also matters for the decision that we're going to make. So if I use the orange quantile averaging method, my estimated risk of exceeding hospital capacity is less than 1%. But under the blue probability averaging method, this risk is estimated to be about 8%. So I make a different decision depending on which aggregation method I choose. So clearly which method I choose matters for the decision, but I still haven't told you how we choose which one, especially when we don't have observations. So what we did in the case of the scenario modeling hub is we dug into the assumptions that underlie each of these methods, and we hypothesized about which of those assumptions was better suited for our particular context. So if you notice, the orange quantile averaging aggregate falls in between the two black individual distributions. The reason for this is because the orange method assumes that individual predictions are like noisy samples. So each of the individual models are sort of imperfect representations of the distribution that we're trying to represent, and so this intermediate aggregate is the best. On the other hand, the blue aggregate distribution is multimodal, and the reason for this is because the blue method assumes that individual predictions are like alternate futures. The world could unfold according to model A, or it could unfold according to model B. We're just not sure which one. So the COVID-19 forecast hub uses a variation of the orange method, and we built a lot of our infrastructure off of the forecast hub, and so this was a very natural starting place for us. But through this work and through thinking through these different methods, we switched and hypothesized instead that the blue probability averaging method was better for the scenario hub and the scenario projection context. The reason for this is we're making projections 6 months into the future, and the models that are making these projections can be quite different. And so we think it's more likely that a single model represents one or a few ways in which the world could unfold, rather than capturing all of the possible ways in which the world could unfold. So now that the hub has been running for over a year, we can think about how we actually test this hypothesis. So what you're looking at here is the observed incident hospitalizations for COVID at the national level, and each point on this graph represents the start of one round of projections from the scenario modeling hub. So what we can do is we can go back and retrospectively aggregate those projections for each round using both methods, and here's what we get. So a couple notes before I talk about what we're looking at here. You'll notice first that rounds 8 and 10 have been excluded. These were internal training rounds. But the other thing is, if you recall from Rebecca's talk, for each round of projections, the models make these projections for 4 distinct scenarios. And here I'm only showing you one. So before looking at any projections or any data, what we did is we decided which of the 4 scenarios for each round was most plausible, was closest to what actually happened. So for example, if a scenario specified vaccine uptake, we then went and looked at the vaccine uptake data to decide which of the scenarios was closest. It turns out that our conclusions are kind of robust across the scenario that we pick, but here we're looking at the most plausible scenario. So one thing to just notice visually is that the blue probability averaging method gives us much wider projection intervals than the orange quantile averaging method. But if we want to think about a more quantitative comparison of these two methods, we can use a metric that's called coverage. And here we'll use the coverage of the 90% projection interval. So I've simplified those aggregates that I showed you on the prior slide to just the 90% projection interval, which is shown here. So to calculate coverage, we count the number of observations that fall within the particular projection interval. So we're comparing the black line, which are the observations, to the 90% projection interval, which is the ribbon. And because this is a 90% projection interval, ideally 90% of the observations will fall in the ribbon. So this is the results at the US level, but we also have projections for every single state. So we can replicate this coverage calculation for all of the states. And when we do that, we end up with a distribution of coverage values. So here's the results for round 1, the probability averaging method. That distribution across all the states is summarized here. We can also do the same thing for the quantile averaging, as well as for the individual models that underlie each of these aggregates. And here's the results for round 1. But the cool thing about the scenario hub is we have many rounds of projections, and each of these rounds is sort of like a replicate of the projection process. So if we look across all of the rounds, we can notice a few things. First of all, if we compare the blue and the orange to the black, we can notice that the aggregates have coverage that's better than most, if not all, of the individual models. And in fact, we talked about this before, but if I were to overlay which individual model is doing best in each round, it would not be consistent. The second thing to notice is that the coverage of the blue probability averaging metric is higher than the orange quantile averaging method. And that's because, and in most rounds, this higher coverage is a good thing, and it makes our coverage closer to that black horizontal line, which represents the ideal 90% value. So today I've talked a lot about using multiple models and multiple projections about the future and how that can be useful. And part of the reason this is useful is because the aggregation of those predictions is robust and reliable. And we're seeing that even in this longer term scenario projection context. But how we actually do that aggregation really matters. And the work that we've done here has given us sort of a framework to think about this problem, even when we don't have observations that we can use. There are a lot of people that I need to thank for supporting this work, including collaborators and the members of the Scenario Modeling Hub, as well as our funding sources. And thank you for listening. I will take any questions.
Awesome talk, thank you.
Yeah, thanks.
So when you were just talking about coverage, you talked about comparing quantiles to data. So how does that work when with, as we all know, most of our data isn't actually the true number of cases? So
yeah, that's a really good question. So we project reported cases. So in theory, our projections could match the data that we observe. But the thing that's really challenging about evaluating scenario projections is that these projections are conditional on particular scenarios, and those scenarios are very rarely realized in reality that the observations come from. So we're thinking really hard about this scenario evaluation problem, and we're far from the answer, but yeah, thank you for asking.
Hi, it seems like the blue method has a greater degree of uncertainty in its predictions than orange, so intuitively then it would have higher coverage. Is there a way to maybe account for that or penalize it for that such that you get how good is its coverage compared to its uncertainty? Yeah,
so the coverage metric does not penalize for having very wide projection intervals. But if you think about it intuitively, a wide projection interval that's too wide is not useful. So we want to be able to capture the observations with an interval that's as narrow as possible. So there are other metrics that we can use, different scores that will actually penalize when we do these evaluations. And when we do that, we sort of see that the blue method is still generally better, but it can be too wide in some cases. And so we actually use a different weighting scheme to account for this really wide projection intervals that we sometimes get with the blue method.
Go along with that. I'm not that familiar with kind of these metrics, but with the 90% coverage, so the best coverage would be 90%, so the best coverage would not be 100%.
That's right.
And so you're effectively kind of penalizing for kind of that, that breadth, right? So
Yep.
Basically, if you have a completely uninformative model where everything is blue across the board, you're always going to get 100%, but that's too high, right?
That's
so
right.
90% coverage is you want to hit that, you don't want to go above it.
That's right.
Okay.
Yeah.
Great. If there aren't any other questions, thank you.